the, this is the lecture, digital image processing, lecture number 13. And previously, I talked about the Fourier transform for the two-dimensional image processing. Now I'm going to talk about other type of the separable transform, which is like this T from F to T, from fx to tu. And here kernel is G, not exponential. So in this case, G can be any function that I will tell you in later in the detail in first slide. Show you here, for instance, this is the transformation, one-dimensional and inverse transform, and inverse transform, and then uh, and for two-dimensional, discrete two-dimensional from 0 to n, and because it is separable, so both kernel G and G1 and G2 is same, so they are same in G, and then it can be any function. I will tell you in detail. This is double summation, and then so in matrix form we have the image F and we have the transformation A. A is of the coefficient of the transformation. For instance, it can be any function, and then transform is here. And back to the inverse is this. For this is the kernel, here is the kernel is this one. So in special case, there is Walsh Transform. I will show you later in this one. Let me show you here. This is here, and this is the transformation in matrix form. So, and if it is for obtaining the reverse transform, we have to use the coefficient, the matrix A, which is coefficient matrix, inverse of that matrix, B, so multiply by both sides, so we get the original image from the transform. So is F is BTB. And if B is not exactly the same as the inverse of A, so it is almost the approximation of this. So we have different kind of the transformation. First is Hammer. No, first is Walsh Transform. Let's go back here. So first is Walsh Transform. For Walsh Transform, we have the, first I will explain and then I will come to camera. For Walsh Transform, the kernel is like the -1 to some power. One dimension, for instance, this for n, very small dimension, 4 dimension, for instance, n is 2, 2 power 2. And then this is the, so the coefficient of W0, that's a Walsh coefficient from here, then just multiplication of -1 to some power. And its power is Bix and Bi 2 minus 1 minus I. So what is the difference here? For W0 means that the B is the, here I explain here, B is the Biz is the case it's in the binary representation of Z. So in this case, if Z is, for instance, 6, then binary is 6 is 110, so B0 is 0, B1 is 1, and B2 is 1. Back to here. And then, for instance, for W0, we calculate is all summation, and for W1 is 1 summation, 1 add, and 2 minus, because we calculate this power of -1. And then for W2 is plus, minus, plus, minus, and W3 is plus, minus, minus, plus. As we see, the highest the highest rotation, I mean, changing is not at the end, at the highest frequency, rather it's in the middle. For instance, number two. Later, I will show it's like this. For instance, if you for N8, X is 0 to 7, U is 0 to 7. And then you can see here the first component is all plus, the second component is plus 4 minus, second component is double plus minus plus, and third component is this. And number four component gives the highest frequency plus minus, and but which is not order actually. The kernel is not order. If we want to make it order, later I will explain about that. And for two-dimensional, of course, two-dimensional also, we have two-dimensional xu and yu, and then just pi is the multiplication of -1 to so we calculate G and H the kernel, and kernel is just plus minus, and then two-dimensional Walsh transform like this and inverse. I can show you in two-dimensional is like this. Here is from 0 to 3 and 0 to 3, and this is for V and this is for U after transformation. So you put the image to the measure image to 1. It is 4 by 4 pixel. So it's all is plus. So it's all is added. Here is half plus half minus. Here plus minus in horizontal. And here is like this and so on. As we see, number two is highest frequency, which is not order, is not here, for instance. 3 is not higher. Later, I will show you Hammer transform and later order Hammer. Let me back to this first and then, okay. And this is from here and then I want to show, go back to camera very soon to explain. Here is the two-dimensional. If you put the image over this 4 by 4 pixel image, and then just white per person multiply by plus, minus plus multiply by minus, and then add, and then you find the coefficient of the transform of, for instance, Walsh. Then now I would like to go back to camera, which here I have to stop sharing. Then I can stop sharing. I can stop sharing. So camera will, I think, will come here. So here is the other type of the DIP lecture number 13. This is the T transformation, A, T, F, T, and B is the inverse of A. So it is P, T, B, T, B is B, A, F, E, B. So if it is exact, B is inverse, so it is okay. Otherwise, it's with the abbreviation. So for Walsh transform, for M, for instance, 4 is 2 by 2. So for Walsh transform, here is summation discrete. 0 to n, large N, fx, pi is multiplication of minus to some power of 2b. Each b means that bkz means that k bit in binary representation of number z. Binary representation, for instance, z is 6, binary representation is 1. 1, 1, 0. So b0 is 0, b1, and so on. So, and then I show you, as I show you the, I don't want to return here, maybe it cannot show again because I have to stop sharing. I have to go to sharing, but I stop sharing here. And then I stop here for Walsh Transform. Later I will explain about the Hammer Transform. So this is the number 13, Walsh and separable transformation and Walsh transformation. And thank you very much. So stop here. I stop recording.